So let me. Welcome everyone. Happy New Year! First of all, welcome to our first talk of this term. If you're not on the mailing list, please send me an email. I can add you to the mailing list, and you'll get all the talks going forward. It's a great pleasure today to have Chen Wang with us from the University of Exeter. Chen worked with Neil Baumforth at UBC. That's where he did his PhD. And he worked on climate type problems that he's going to tell us about. And his talk, I think you got rid of the shared screen. And do you want to start? But
okay.
you have to.
I can start now. Yeah, I will share it again.
Yeah, share it again, and we can go.
Okay. Thank you for coming to my talk. And now I will start. And my name is Chen Wang. Now I am a postdoc research fellow at the University of Exeter. Now I'm working with Professor Andrew Gilbert and Dr. Joanne Mason on waves and instabilities in MHD system. So on this work, I'm going to talk about today, nonlinear dynamics of false baroclinic critical layers is my PhD work at the University of British Columbia, working with Professor Neil Baumforth. And first, I'd like to thank Professor Zhuzong Wu. He reviewed my PhD thesis with great detail and gave me a lot of helpful comments. And he invited me to here to give this talk. And it's an honor to give this talk here. And so now I will get started. So the background of our research comes from the protoplanetary disks. So before a star forms, there was a very large disk composed of very sparse gas and dust. And this disk will gradually create mass onto the star at the center. And this process is an important process in the star formation. And how does the disk accrete mass or fall onto the star is still an open problem. So people think there must be some instabilities in the disk that drives this accretion. And so what is this instability still remains to be understood. And there are people have proposed many possibilities. And among these instabilities, the magnetorotational instability is perhaps the most popular one. And but at some situations, the magnetic field can be weak. So people also consider other instabilities. And the instability I'm going to focus today is called the zombie vertex instability. And okay, so now let's look at the zombie vertex. And zombie vortices were discovered by Marcus and his colleagues in this paper. And they found that in rotating stratified shear flows, vortices can replicate themselves. So initially there are some vortices here, and the vortices will excite the baroclinic critical layers, for example here. And the critical layers will roll up and excite new critical layers, and this process will repeat. So finally, the entire domain can be filled by these vortices and critical layers. And we see that the replication is accomplished by the excitation of these, what we call baroclinic critical layers. And we want to study and understand this phenomenon theoretically. So we mainly use the method of matched asymptotic expansions. And so first, let's briefly introduce a critical level and critical layer. So basically, if in the basic flow, we have a shear, and we also consider the plane steady waves propagating in the shear flow. And if the fluid is inviscid, then at some specific levels, which we denote as YC here, the plane wave solution can become singular. And the most common type of classical critical level is what we call the classical critical level. It is the location where the basic flow velocity matches the phase velocity of the wave. And the critical level we are going to talk about today is a different one. It is what we call the baroclinic critical level. It happens in stratified fluid with horizontal shear, and its location is where the phase velocity relative to the basic flow velocity matches the characteristic velocity of the internal gravity wave. So here, this big N is the Brand-Väisälä frequency, which represents the density stratification. And this K is the horizontal wave number. And in order to resolve the singularity at the critical level, we need to consider either viscosity, nonlinearity, or unsteadiness of the wave. And but even if we consider these factors, there are still large amplitudes in the critical layer. And so in our study, we will go down the line of the unsteadiness. And this is because at the beginning, the nonlinearity can be weak. And also, initially, there is no disturbance. All the disturbance can have a relatively large gradient, so viscosity can also be weak. And also, at least in the simulation of Marcus, they claim they were studying the inviscid fluid. But at the end, we will include all these factors. So now we look at the typical paradigm or models for the unsteady critical layer. So the first model, the typical approach is to consider an unstable mode. So if the flow is unsteady, this means the phase velocity, which appears as an eigenvalue, has an imaginary part. And so this imaginary part can avoid the singularity because the basic flow velocity is always real. And in this way, we avoid the singularity. And but this imaginary part can be small. So here in this critical layer, we still have locally large gradient. And this is an example of an unstable mode. And the second way to consider the unsteady critical layer is as we consider the forced waves. So this happens, for example, if a shear flow pass a wavy topography, for example, past the mountains, and these mountains will force the waves. And these forced waves have zero phase velocity. So, and if the phase velocity is zero, we don't have an imaginary part. And so what happens in this critical layer is that in the local region of the critical layer, the flow remains unsteady. Outside the critical layer, the flow is steady. And inside the critical layer, as this figure shows, the amplitude will first increase and then it will become nonlinear. And the third typical model of considering the unsteady critical layer is to consider a wave packet. This happens, for example, in this figure, we have wave packets approaching this line, the critical level. And as it approaches, the linear theory based on retracing will tell us that the amplitude will increase, the waves will become shorter, and it cannot pass the critical level. It is trapped by the critical level. And finally, it will become nonlinear, of course. And so these are the three main models for the unsteady critical layer. And so after some consideration, after a lot of trial and error, we found perhaps the second model, the forced wave, is more appropriate. This is because for the instability, the basic flow of the linear shear, which they consider is stable, so we don't have an unstable mode. And for this paradigm, the wave packet one, for the zombie vortices from the initial vertex to the critical level, the disturbance are not like this wave-like. It is evanescent, so we don't have wave packets. So and now, sorry, but for this one, we do have an initial forcing. we don't have topography, but we need an initial array of vortices that excite the waves. So we can do this. So now now let's go to our model. And as we said, our paradigm is the baroclinic critical layer of fault waves. And this is the model of our study. So we consider, for the basic flow, we consider a horizontal shear flow. The basic flow velocity u is in x direction, and it has a shear in the y direction, both in the horizontal plane. And the shear rate is this lambda. And we consider a density stratification. So the Brand-Väisälä frequency is this big N. And this curly N is the Brand-Väisälä frequency scaled by the shear rate. And we also consider a planetary rotation, this F. The dimensionless parameter, dimensionless Coriolis parameter F is the 2 times angular velocity divided by this shear rate. And as we said, we consider the false wave. So at y equals 0, we impose a weak falsing. This falsing is periodic in both x and z, and the ratio of the wave numbers we use as a dimensionless parameter f. And once it is turned on, it remains steady. So it falls steady waves. And this is our model. And in this figure, we see here and here, we see locally large amplitudes. And this is the baroclinic critical layers we are going to study. So these are our Gaussian equations. We use the Boussinesq approximation for the disturbances. So the density affects the buoyancy term. Affects the buoyancy, and the buoyancy term is here. In the momentum equation, we neglect the in these momentum equations, we neglect density. We only consider it in the buoyancy. And this equation, the evolution of the density, we have this term which represents the advection of the basic density stratification. And finally, we assume it is incompressible. And initially, we consider there's no disturbance. So at t equals 0, all the disturbance is 0. And then at t larger than 0, we turn on this falsing. And what this falsing does is it generates a jump of the tangential velocity. So which means this is a vertex sheet. So it is an idealization or an analogy of the actual zombie initial vortices in the zombie vertex phenomenon. And yeah, this is our equations. And then we solve these equations. So in the earlier stage, the disturbances are small, so we can consider the linear theory. And also, because as we said, once the falsing is turned on, it remains steady. So after a transient period, the falsing will false steady waves through the bulk of the flow. And so in most regions, we can have this steady wave solution. It is steady, so the phase velocity is 0, and the waves are periodic in x and z. But in the y direction, because we have a shear, the disturbances may not be wave-like. And then we substitute this expression in the Gaussian equations. We can derive this second order ODE for the pressure, and we can solve it. And the solution looks like this. So we see, so here at y equals 0 is where we impose the falsing. The falsing makes a jump of the gradient of the pressure. And here and here, we see that the pressure its derivatives kind of become discontinuous. And these locations, y equals plus or minus this curly n is the baroclinic critical levels. And from the equations, we can see that we also see that we have singularities here. And if we can analyze the Frobenius solution near these two critical levels, and we can show that the pressure itself doesn't diverge, it converges to a constant, and we denote this constant as A, and we say its absolute value or norm is a small number epsilon. And the pressure itself doesn't diverge, but we see its derivative kind of become discontinuous. And we can also show that all the other components, the velocity and density, they all diverge at the critical levels. So at the critical level, we see that the steady wave solution fails. So in the critical level, what we do is, as we said, the critical layer is unsteady, so we restore the time dependence. And so for pressure, because the outer solution doesn't diverge, so and also because the critical layer is very thin, so we can use its outer solution, which is a constant in the very thin critical layer. And but for all the other disturbances, we use these tilde variables, which are functions of time. They are unsteady. And so here we write down the equation of vertical velocity and density. The two are coupled together by buoyancy and basic stratification. And then we can derive one equation for density. Oh, sorry, here. This should be a row term here. Yeah, sorry, I forgot it. And then we can solve the equation of the density. Yeah, it looks like this. So so from this solution, we can show that first what we see is if you don't have the time dependent term, it becomes singular. But once we add it, when we add the time dependence, the unsteadiness, the solution is no longer singular. And also, we can show that as y becomes very close to n, there is a secular growth. So the density will grow linearly with time. And also, from this term, this combination, we can show that as time increases, the critical layer, the thickness of the critical layer will become thinner and thinner in the manner of 1 over time. So the picture of the linear critical layer is that it will gradually become stronger and thinner. And this is also the result of the picture in other unsteady critical layers, for example, the Rossby wave critical layers. And yeah, and we can also show that other disturbance, for example, the vertical vorticity also has this kind of secular growth. And why does this happen? We can interpret this as a resonance between the forced waves and the internal gravity waves. So we can see that the homogeneous part of these two equations have a frequency or phase or velocity y plus or minus n. So n is the characteristic frequency of the internal gravity waves, and this y is the basic shear. And on the right hand side, this pressure, and this pressure is phase velocity is imposed by the forcing, which is 0, because the forcing has 0 phase velocity. So we see that at y equals plus or minus n, the two become the same. So we know that if the forcing has the same frequency with the frequency of the homogeneous system, there can be a resonance which makes a secular growth. And this is the reason why we have this secular growth. And then we consider that the forced secular growing disturbances can generate mean flow response. So now we consider the mean flow response of these waves. In the expression of the disturbances, we add this mean flow response, these 0 terms. And we will mainly focus on the streamwise mean flow distortion. And this is the original equation of the streamwise momentum. And we substitute this expression into this, and we select the mean flow component of this equation, and we have this mean flow response equation. So it describes that this the forcing of the waves, the forced waves can force the growth of the mean flow distortion. So we can solve this U0, and we have this expression, and we can show that, and it has a faster growth, although it has a smaller initial amplitude. Yeah, and then now we plot the entire vorticity of the vertical component. So so in the earlier stage, we have a linear critical layer. So the vorticity also grows like this, and it is linear waves, periodic in X. And as time increases, this mean flow response will gradually become stronger. And so we see that finally the vorticity become nearly homogeneous in the streamwise X direction. And we can also show that this happens even before the forced wave become nonlinear. So the mean flow will dominate at the earlier stage. And we can also show that the harmonics remain weak. We don't see higher order undulations. And this is a special characteristic of the baroclinic critical layer, because by definition, the critical level depends on wave numbers. This means higher order harmonics, which have different wave numbers, they have different critical levels. So they are not sufficiently amplified in this critical level. And that's why they are not strong enough here. And then now we can have a look at the numerical simulation of markers. This is their full simulation, an example of this full simulation. And we see at earlier stage, they have periodic waves. And then the wave become nearly the pattern become nearly homogeneous, means the mean flow become predominant. And these two patterns are very similar to what we just saw. So we think we have good agreements in the earlier evolution. And then what happens in their simulation is that we see this negative part of the mean flow vorticity will roll up into a larger vertex, and this vertex will gradually expand. Yeah. So we want to model, we want to analytically describe this phenomenon. So we consider this problem. And so there are two possibilities. Of course, we need to consider some new nonlinearities. And the first possibility is that, so here we are considering the linear forced waves and the mean flow response generated by these linear forced waves. So one possibility is that these forced waves, these mean flow responses can also feed back to the linear waves. And this will make the critical layer nonlinear, these waves nonlinear. And the second possibility is that this mean flow distortion, it has a very localized large vorticity gradient. So this can become unstable. So maybe this instability will cause this kind of roll up, and we look at them one by one. So first, let's consider the feedback to the fundamental wave. So now the mean flow has two components. One is the basic linear shear, and the other is the mean flow response of the linear forced waves. And we can derive a modified evolution equation. It looks like this. So the left-hand side is, again, the evolution equation for the linear density, but the right-hand side now represents the feedback of the mean flow response. So this U0 is the mean flow distortion, and we can deduce how fast it grows. So for example, this density grows linearly with time, and the mean flow distortion grows in epsilon square t square. So we can show that at this time, when t is in the order of epsilon to minus 2/3, this nonlinear feedback will become as strong as the linear terms on the right-hand side. And at this time, the secular growth of the linear forced wave will be modified. Yes, and it will evolve in a nonlinear manner. And we have considered this model in detail in our previous paper. Yeah, and the second possibility, as we said, is secondary instability. So in this figure, we have plotted the basic shear with the mean flow distortion. So we see that the mean flow response in the critical layer generates this small defect. This defect is weak compared to the basic flow, but if you consider the vorticity gradient, the second order derivative of U, it can be strong because it has very small spatial scale. And previous study have shown that this kind of stable basic flow with a small defect can become unstable. So it become unstable when the vorticity gradient of defect is in order 1. And now we can we have the expression of our mean flow response of mean flow defect. It looks like this, and then we can show that the vorticity gradient grows even faster because the length scale of the critical layer is small. So it grows in epsilon square and t to 4. And then we can find that when t is in order epsilon to minus 1/2, its gradient, the vorticity gradient will be order 1. And the important thing here is that this time is earlier than the time when the forced will become nonlinear. So so this means the instability will happen when the critical layer, when the forced wave itself is still linear. So now in this talk, I go on this line, secondary instability, instead of the feedback to the fundamental wave. So we consider this instability. So first, let's give a heuristic explanation of this instability, why a defect can make flow unstable. So we use a normal mode to explain this. So strictly speaking, the instability may not be in the form of normal mode. This is because the basic flow defect is unsteady. But nevertheless, we do this to give a qualitative explanation. So we consider the normal mode on this basic flow with defect, and we solve this normal mode. And this is what the unstable mode of pressure looks like near the critical level. So in order that it is an normal mode, it must decay to 0 at both y goes plus or minus infinity. And if you don't have the defect, this can happen only in one of the limits. For example, this p minus decays to 0 as y goes to minus infinity. And this t plus goes to 0 as y goes to plus infinity. In the other limits, they both diverge. And what this mean flow defect does is that it can connect these two pieces. So in the mean flow defect, we can show that pressure has a similar form with Rayleigh's equation. It is proportional to in order of vorticity gradient over U minus C. And if we integrate this thing over the critical layer, and it can give a jump of the gradient of pressure. And that's why we see we need this U mean flow defect vorticity gradient to be strong enough. Yeah. And we can also, there are some also important properties of this instability. So first, the phase velocity, its phase velocity is very close to this curly N, the critical level, or the phase velocity in the critical level. And this is because in this expression, this Y is close to n. And so only when C is also close to n do we get a sufficiently large jump of the gradient. And also we see that in the critical layer, pressure itself is nearly a constant. And this also applies to the cross-stream velocity V. And we can also show that now the vertical velocity is small. This is because this is mainly a horizontal shear instability. And then with this information, we can now build a reduced model to more rigorously understand this instability. So first, we do a number of rescalings. So we have shown that at this time, epsilon to minus 1/2, the critical layer becomes nonlinear. Sorry, the secondary instability will commence. So we rescale time by this scale, and we use this big T, the slow time, to represent the evolution of the critical layer. And similarly, we introduce the big Y to represent the stretched coordinate in the local region. And we can find the scale of the mean flow defect and the density, and we rescaled them into this curly U and curly R. And now at this stage, we introduce the viscosity nu and the thermal diffusivity kappa. And we can show that at this order, epsilon to 3/2 at this order, their effect is at the same order with other terms. So we consider we consider them at this order, and this mu and this lambda is the rescaled viscosity and thermal diffusivity. So we can derive the equation for density and the mean flow defect in terms of these rescaled variables, and we can solve the mean flow defect. It can be represented by this integral solution. So if there is no diffusivity, diffusion or viscosity at all, then as we previously shown, the defect will grow in order t square, and its length scale will gradually become smaller. And if you have only thermal diffusivity, the defect grows slower, linear with time, and the length scale will not shrink. And if we also have viscosity, the defect will grow even slower, the square root of t, and its distribution will gradually spread out. Yeah, but the important thing is that at this order of dissipation, it does not stop the growth of the mean flow defect. The mean flow defect keeps growing. And then now we consider the unstable disturbance, the disturbance for the instability. And first, we consider, now we formally use the matched asymptotic to consider the instability. And in the outer solution, disturbances are characterized by the quasi-steady waves. So we, similar to the first wave, we have this steady wave solution. But now the important thing is that the phase velocity is now this curly n. It is no longer 0. And and the amplitude is a function of y, and we can solve it. And the solution, the pressure looks like this, similar to the first wave. But now the discontinuity of the gradient happens at y equals curly n, the critical level, not 0. And so we see that, and here at the critical level, the inner solution will drive this jump of gradient. And also in this steady wave solution, we have a slowly varying amplitude, and this phi for each Fourier component. And it is determined by the slow variation of the critical layer. Yeah, that's why we say it is quasi-steady. It is driven by the critical layer. And in the local region, we do a local analysis for the instability, and because we show it is nearly the leading order dynamics is nearly two-dimensional horizontal. It is characterized by horizontal shear instability, so we can have a stream function. And in the critical layer, because now it is the classical critical layer for the secondary instability, so we include all of the Fourier components. But all the Fourier components have this phase theta and have this phase velocity curly n. And then we can derive a volticity equation. This is the main equation we are going to solve. And so the volticity varies with the slow time. It is affected by this term, which represents the linear shear, and this term which represents the advection of the volticity gradient. So the first, this term is a nonlinear term, and the second is the mean flow volticity gradient. And we also consider this diffusion. This viscous term. And the last equation of the reduced model is the matching condition. So it tells us that the overall integral of the vorticity should match to the jump of the velocity of the outer flow. And this can be linked to the jump of this of the gradient of pressure in the outer region, this jump of gradient. And this is how the critical layer will drive the slow variation of the outer flow. Yeah. This is our equation for the reduced model. And at this point, we can consider the effect of unsteadiness of the basic flow defect more rigorously. Yeah, so now we solve the equations. So again, first we start with linear instability. So if it is if at the earlier stage the flows are small, the disturbances are small, so we can consider linear instability. We can consider only one Fourier component, and we use this one to represent n equals 1, and they have wave number k. And so we neglect this nonlinear term, and we derive two linearized equations, and we can solve them. And after some algebra, we can derive an integral equation for this stream function psi, and we can do some analysis to it, and also we can solve it numerically. So we can show that if we do not have dissipation at all, we can derive an ODE for this stream function. It is fourth order, and here in this term we have a t in the coefficient. It looks somewhat like an array function, and this delay term represents function of an earlier time, which is unimportant because it is small if the disturbances grow exponentially. And then we can, and as we see, it's similar to an array function, array equation. So we can derive a WKB solution for this ODE, and it looks like this. And so the important thing here is that because the mean flow is unsteady, it keeps growing. So the normal mode, the instability is not in a normal mode form. You see that it does not grow exponentially with time. It grows exponentially with time to a power of 4/3, faster than a normal mode. And also this growth rate, it diverges if k goes to, the wave number goes to infinity. This is also the effect of the unsteady basic flow, because the defect becomes thinner and thinner. So the larger wave number will be selected. And this means there is an equiposeness of the, there can be an equiposeness of the implicit of the non-deceptive limit. So in the actual nonlinear evolution, we always need to add a little bit of dissipation. But anyway, this is what the non-deceptive limit looks like. And then we consider the effect of dissipation. So we go back to this integral equation, and we can do some analysis and solve it numerically. And the result is that if you only have thermal diffusion, the thermal diffusion will only delay the growth of the disturbance. As it becomes larger, the diffusivity becomes larger this growth will start later and later, but finally it will grow as if there's no dissipation. And if you have viscosity, then it has a strong stabilizing effect, stronger effect. So if you increase viscosity, the disturbance will grow slower. And if it is too large, disturbances will decay and the instability is suppressed. And this is the result of linear instability. And next, we solved the nonlinear evolution equation. We consider what happens after the disturbance become nonlinear. And these two equations are the evolution equations. So this is the nonlinear term. And so our numerical method is that of Chen and Nor. And this is efficient in solving this kind of a convection problem, because in this method, we do not use finite difference to approximate these two spatial derivatives. Instead, we do advection. So in each time step, in the first half step, we advect the vorticity in theta direction. And in the second half, we advect the vorticity in y direction. And so we only need to do interpolation to find where we should advect from. So this is more efficient. Yeah, and we can, for the initial conditions, we consider two kinds of excitations. So first is one net with only one Fourier mode in theta. And the second one is in theta, we have a Gaussian distribution. So it excites a broad band of initial disturbances. And this is an example of the evolution of stream function. So the dotted line is linear solution, and the solid line is the nonlinear numerical solution. And so in the earlier age, the nonlinear evolution just followed the linear growth, but when it becomes large enough, the disturbance, the growth will be saturated. And in this small inset, we show the result plotted in the regular scale instead of the logarithm scale. So what we want to show here is that even after the exponential growth saturates, there will be another slower cyclic growth. Yeah, and this happens is again because the mean flow keeps growing. This drives this smaller cyclic growth. And then we look at the evolution of the vorticity. So first, we consider one for the single mode excitation with medium high viscosity. So the first three figures is the Faust linear waves and the mean flow defect, which we have seen previously. And then in this figure, we see there is a wave developing on the defect. And this is the linear sector instability. And then as the disturbance grows stronger, we see the nonlinear effects. And then we see that, and then as time further increase, we see it will roll up into a below, which is typical in shear flows. And finally, because of viscosity, the belows will gradually fade. And we have a large negative vertex here, accompanied by a shear layer. And if the vorticity is stronger, so what we see is the belows will become shorter and fade more quickly, and the final vertex will become larger. And then we consider what happens if the viscosity is very, very small. And this is the result. So we still have the rolling up of the below, but now because the vorticity is too small, so the viscosity is too small, the belows become thinner and thinner and does not fade. And when it becomes thin enough, it can have very large vorticity gradient. So these thin belows become unstable again. So we see even smaller belows, smaller waves develop on these belows, and they will roll up. And then finally, some mixing event will happen. And at this stage, this very small viscosity will come into effect and diffuse away these very small vortices. And again, we have a similar structure that is a large vertex accompanied by a shear layer. And finally, we consider the result of multiple mode excitation. Initially, there's a broad band of wave numbers. And so as we expect, we see multiple billows will develop, and they will interact with each other. And so they will, first two of them will pair and merge, and then the other one will also pair and merge. So finally, they will again merge to one vertex, a similar coherent structure. Yeah. And finally, we review the story and show how it can explain the replication. So what we did is initially we put a falsing here. This falsing will false the linear critical layers. The linear critical layers will develop mean flow defect, and the mean flow defect will roll up by a secondary instability. And as we have been emphasizing, this secondary instability has a different phase velocity, this curly n. So this means it will have different baroclinic critical levels, which we plotted here and here. And these new baroclinic critical levels will repeat in the same way as the original ones. And this will, so they will have mean flow defect and roll up again, and this will make the process repeat itself to replicate. Yeah, and yeah, and that is also for my talk. Thank you. This is me and my supervisor after my PhD defense. Yeah, I'd be happy to take questions.
Thank you very much, Chen, for really beautiful talk. Fascinating results. Thank you. So we can open the floor to questions. Okay, I'll ask one to get everyone going. When you do this initial forcing, it's a vortex sheet type forcing, right? There's a slip velocity.
Yes.
Now the time to a more singularity of a vortex sheet will be of order log epsilon, log 1 over epsilon, which is much smaller than the algebraic times you're getting for the formation of the critical layers. Is that something to worry about?
Yes, that is something to worry about, but yeah, but I mean, so in their simulation, for example, in the simulation of Marcus, what they did, what they put here is a number of periodic Gaussian vortices, and those vortices will of course they will evolve, but our vertex sheet is somewhat idealization of their model. So we don't care about how the forcing itself at this point we don't care about how itself evolved, but we know that it as long as it is strong enough, it can survive for a sufficiently long time, and that is enough. So we consider what if we just have a static forcing, what it does. Yeah. Of course, the more realistic forcing is a problem to consider. Yeah.
So if you did, because you didn't do full simulations of the whole thing, right? Otherwise, you could get other effects. Yeah. Okay.
Yeah, I think it is an interesting problem to study if you replace this idealized forcing with some more realistic, for example, like some actual vortices, and consider the effect of the evolution of the vortices themselves. I think it should be an interesting problem. Yeah.
Mm-hmm. Thank you. Yeah. Any other questions?
Yes, I have a question.
Yeah,
I'm Patrick Huer from Paris, and I was told that there would be an interesting talk today, so that's why I'm here. I spent some time with Phil Marcus in Berkeley some 5 years ago. I was fascinated by your talk, Very, very, very impressive work. I wonder why the classical scaling for nonlinear critical layers, a la Bailey-Bergeron, why it allows you to unravel this replicating process. How did you come with this idea that compared to your earlier paper, that you should catch the evolution at some earlier time to try to reveal this secondary instability and the self-replicating process? Can you elaborate on this for a little bit?
Yeah. Thank you for your question. Yeah, as you know, in our previous paper, we were considering the fundamental, the feedback to the fundamental wave. That is, if the wave itself becomes nonlinear, what's its evolution? But we found a lot of interesting phenomena. We derived a compact mathematical model, but at the end of the day, we didn't see what happens in their simulation. So we believe something is missing. Yeah, and then Neil noticed that this basic flow velocity is unstable, and he did some in his previous study. He knows that when it becomes unstable, and then we compute, we analyze, and we did find that this instability happens before the waves become nonlinear. Yeah. And then so we go along this way, and actually, unfortunately, a lot of this analysis may not be very relevant, because it happens after the instability, the instability becomes prominent. Yeah.
Mm-hmm. Mm-hmm. Yeah, very interesting.
Oh, thank you.
Yeah, great. Stephen, you have your hand raised.
So how does the short question is, how does this relate to Kilworth and McIntyre? Because they looked at instabilities of weak defects as here, back in what, 85 or something like that. Yeah. So is this essentially the same mechanism that Kilworth and McIntyre looked at?
Okay, yeah, I should say that the basic idea is similar, because they also consider after the nonlinearity becomes significant in the critical layer, or before it become, or even when the critical layer is linear, the mean flow, it can be unstable. The critical layer can become susceptible to a new instability. I mean, this is similar, but there are still some differences. So first, I think the first thing is in our problem. So as we show here, for example, in this picture, in this figure, for the baroclinic critical layer, the mean flow defect is predominant, but in the Rossby wave case, what we see is some pattern like Kelvin's cat's eye. It has all the harmonics. So and this is one difference. And so second, because they have all the Fourier components, what it was, but you need to consider the instability. So they need a scale separation. That is, the instability, the wavelength of the instability should be much smaller than the characteristic wavelength of the Kelvin Hertz eye. Otherwise, you don't need to how to define the mean flow. Yeah. So, but in our problem, because we only have the mean flow as the predominant distortion. So we can just analyze its instability. We don't need another scale separation. Yeah, this is my answer. Yeah, but the basic idea is similar. Yeah.
Another thing Kilworth and McIntyre need is that they need to introduce random amplitude, for the instability. Whereas I think your amplitude comes out of the basic wave, doesn't it? You don't need a set. You've got an evolution. You've got the forcing, and then from the forcing, you don't need another you don't need a secondary instability. In some sense, the instability is forced by the original wave.
Yeah. So yes, yeah. So for the secondary instability, it is not forced by the initial wave. Yeah, and
is it forced by the initial wave, or do you need a separate instability amplitude?
The amplitude is free from the original forced wave. Yeah, it is affected by the mean flow, the mean flow vorticity gradient.
So where do you get your initial amplitude from for the secondary instability?
Yeah, because yes, as you said, yes, we don't know. This is an issue, but at this time we just show because it's linearly unstable. So we just show that for any kind of initial disturbances, because it is unstable, they can grow. Yeah.
It's unpublished, but I had a student work on the fact that you can show that the initial, for Kilworth and McIntyre, the original flow actually will generate the instability. So you don't need an arbitrary instability amplitude, and there might be something similar here.
Yeah, I agree, but we haven't considered that yet. I agree, yes, because in the forcing, there are some smaller disturbances we are not included here that can contribute to the initial disturbance. We consider this issue, but we didn't further go on it.
Okay, may I ask a question?
Yeah, of course. Shusong, go ahead.
Yeah, so this initial condition for secondary instability.
We can't hear you very well. Shusong,
yeah.
we can't hear you very well.
Oh, I have a very crappy connection. Maybe. Yeah. Can you hear me now?
Yeah, better.
No?
Yeah.
Okay. I don't know why. Okay, we are talking about instability, sorry. Yeah, secondary instability. So when the defect is weak initially, then this secondary instability does not operate, right?
Yeah. That is what we think. Yeah.
Yeah. So that's why then there is a kind of an issue. In your this distinguished regime, there is no separation between the base flow, the defect, no separation of time scale.
Yeah.
And the secondary instability. So when you go when t goes to 0, I think the secondary instability should disappear somewhere, right? Only when defect is sufficiently strong.
Yeah. We have shown here only defect only 1t is in order of epsilon to -1/2. After this time, the secondary instability the defect will be strong enough for the secondary instability, and before this time.
Yeah, that's asymptotic scaling, but when you cap the t, rescale t, when you do initial value calculation for secondary instability, when you take a t to 0, so then the dynamics may be dependent on the initial condition you choose.
You mean
if you introduce your secondary instability at different instance, right? The point is that you can't have a consistent asymptotic kind of initial condition consistent with the dynamics. Yeah. So these are imposed at certain finite value of capital T.
Yeah, I agree. There are some issue about this, but yeah. But anyway, what we did is we at t equals 0, we impose these disturbances. But so as you said, before the instability, before the defect becomes
the defect is 0. Yeah.
So if there is no because initially there's the defect is too weak. So what happens to these disturbances that is like in this figure, all of them will decay first.
Right? Yeah, there's constant decay.
Yeah. And after the defect becomes strong enough, and then they will grow. Yeah. So here we actually we don't know very well what is happening here. So at the earlier stage, we know it is something like Landau dumping, but how does it start to grow? We still don't know how to describe them analytically. Yeah, but anyway, they will grow. That is our main interest.
Okay, may I ask the other end? Question, when T is large, so here you are taking, you ignored your first issue, the effect on the fundamental, right? The defect itself may evolve non-linearly. So when T is, your secondary instability in a non-linear version can depend on how strong the secondary instability is, the initial condition. By if you choose small initial for your secondary instability, then the nonlinearity of secondary instability will take place at a later stage. So and this T, by that stage, T is sufficiently large, for example, practically to epsilon to minus 2/3, then your defect evolution will follow your first part. So I'm saying you can combine it too.
Yeah. I agree. Yeah. So this
could happen.
I agree. Yeah. So this is in terms of the limit of epsilon go to 0. Yeah. But I agree.
It's still linear.
If actually the instability happens much later, perhaps we need to consider whether this time scale may do something. But actually we did compute, for example, if the defect is fed back by the nonlinear waves, but generally the phenomenon is similar. But there are some other.
The nonlinearity will attenuate effects. Would the nonlinearity of defect itself attenuates itself? So your Osentor is not T, secondary instability is not T to.
Secondary. So sorry, can you say the last question again?
Okay, yeah, the connection is bad. When the defect involves non-linearly,
okay,
I guess the defect would attenuate somewhat, right?
Yes,
T-square is not as fast, and then the secondary evolution, the secondary instabilities, this WKB form would be different, isn't it? You have a okay. The next one.
Yeah, I agree. Yeah, but we did solve that problem. We consider if they evolve nonlinearly. Yeah, but because anyway, if you consider those terms, they will appear. For example, they will appear in a higher order term. Although, so our result is that the basic phenomena is still similar. So for example, if we consider the nonlinear evolution, what happens is this negative one will be stronger and thinner, and this positive vertex will become slightly larger. And but the qualitative figure of this this roll up is still similar, I think. Yeah, but of course, in terms of precision, perhaps that is better. Yeah. I agree. Yeah.
Okay, we have a question by John Mathvan.
Oh, hi. This is John Methven joining from the University of Reading. Thanks very much for allowing us to join these fluids seminars.
Oh, of course, please.
So I had a question about this, actually the picture there, the secondary instability. So obviously the negative vorticity strip rolls up and you get an anticyclonic or kind of negative vorticity larger vortex. Is that because the background vorticity is negative? So, you know, you've picked a state where lambda is positive and the background vorticity is negative.
Yeah, I think so, because the basic flow looks like this. So in the region of negative vorticity, this is what we think. So we think because the shear is stronger, the basic shear is strengthened by the defect. So perhaps this part is easier to roll up. Yeah, that is what interpret as.
But in your initial setup, you also mentioned that you could have background rotation, you know, F, depending on omega over lambda. So if that was the opposite sign to the background vorticity you've picked in the shear, what would happen then?
You mean the rotation?
Yeah, if you were in a rotating frame, yeah. So omega had the opposite sign to lambda.
We didn't analyze it, but in our reduced model, planetary rotation doesn't appear in the here.
Yeah, I noticed that. Yeah.
Yeah. So it only affects, for example, how large is this epsilon. So our preliminary guess is perhaps it doesn't affect whether the other will roll, which one will roll up. Yeah. This is our. This is my current current guess here.
Okay, thank you. Cheers.
Okay, thank you. Any other questions? No. If not, let me remind everyone. Next week's talk is by Camille Duprat from LADIX, and I'm still waiting for a title. So I'll email everyone with the details once I have them. So again, thank you very much, Chen, for a really interesting talk. A great way to start the season.
Well, thank you
again.